Hey guys. All right, so today is our third and final lesson on linear modeling. And in fact, it's our final lesson learning anything new in this topic. Remember, this has been a pretty long topic. We've done two chapters, chapter 3 and chapter 6. This is the final lesson where we learn anything new. For the next couple of lessons, it'll just be a revision. All right. So we are looking at determining the equation of a line of best fit from its graph. Now, we all know how to determine the equation of a line, and if you know how to do that, then you also know how to determine the equation of a line of best fit. It's the same skill. So what we're really doing is looking at a skill we've already learned, but in the context of linear modeling, and in particular in the context of scatter plots. All right, so this set of notes starts off with three definitions. We're going to ignore the second two for a moment. I want to come back to those when we dive into the examples because it'll be easier that way. So to start off with, let's have a look at the first definition. A line of best fit is a linear graph drawn on a scatter plot that represents a trend between two variables. All right, so what does that mean? Well, the best way to understand what that means is to have a look at an example, which is exactly what we're going to do. So the following graph shows the average height h a particular species of palm tree grows to in different average temperatures T. Measurements have been taken from all over the world. So let's take a look at this graph. Now, for a moment, just imagine that this line here, this line of best fit, hasn't been drawn in, okay? Now, each one of these dots represents a measurement that has been taken in a different location around the world. And each one of these measurements has two values associated with it, an average temperature and an average height. Now, let's take a look at this point here. That measurement, let's just make up a location. Let's say, I don't know, Canada. In Canada, where the average temperature is 5 degrees, that's probably wildly inaccurate, but it doesn't matter. In Canada, where the average temperature is 5 degrees, these particular sort of palm trees grow to an average height of 15 meters, okay? Let's pick another random place, I don't know, in Australia, let's say, where the average temperature might be 20, and again, I'm just making this up, this corresponds to an average tree height for this particular variety of palm tree of 40 meters. And if you plot enough points from enough locations around the world, what you get is a scatter plot. And you can tell from the trend of those points that form the scatter plot that there is a relationship. The relationship isn't perfect. Those points don't form a perfectly straight line, but those points certainly are trending in the same direction. And so what the line of best fit does is it sort of averages out that trend. It's simply a line that is drawn in the best way possible in the direction of the trend that is formed by those dots that form the scatter plot, okay? But how did I actually go about drawing this line of best fit, this purple line, you might ask? Well, it's a pretty imprecise science, to be honest. If you input a set of points into a program like Microsoft Excel or even your CAS calculator, then Excel and the CAS software has extremely complicated algorithms that it runs in order to determine a very mathematically precise line of best fit. But when you're doing it by hand, you just eyeball it, okay? And as a rough rule, you want to try and have roughly the same number of dots above the line as you have below the line, okay? So the thing about line of best fit problems is that as teachers, when we mark students' assessments and they've had to draw a line of best fit and then find the equation of the line of best fit, everyone gets a slightly different equation because everyone's going to draw their line in a slightly higher or lower location compared to the next person and with slightly different gradients because it's an approximate thing that we're doing, okay? And that's totally okay. But as a general rule, you want to aim to have as many dots above the line as you have below the line. All right, so jumping into some questions based on this example. Question A, what height can we expect a tree to be that is growing in a region that has an average temperature of 0 degrees Celsius? Well, let's take a look at our graph. When the average temperature is 0, the corresponding average height of tree is 8 meters, and that's pretty approximate, okay? So I think I'll actually remove that equal sign and make it a squiggly equal sign, which means approximately equal to. So when the average temperature is 0 degrees Celsius, the average height is approximately 8 meters. Question B. The slope of the line represents the increase in height of trees per degree Celsius. Determine the slope. All right, well, that's easy enough. We have a formula. Slope, which in our y equals a plus bx is also referred to as b, equals y2 minus y1 over x2 minus x1. So we need 2 points, which I have already added to this diagram. We've got x1, y1 here, and x2, y2 here. Now, here's an extremely important point to note. We want 2 points on our line, okay? Any 2 points on this line. Now, what students tend to do is they use the coordinates of 2 of these dots that form the scatter plot. But we are specifically trying to find the equation of the line of best fit. So we need 2 points that are on the line, okay? So I've just chosen this point here, just because it looks like it has roughly whole numbers as its coordinates, which is 23, 45, but I could have just as easily chosen any other point here, here, anything, okay? You'll still get the same answer no matter what 2 points you choose. So 23, 45, that's my x2, y2, or x1, y1, it doesn't matter. And 0, 8, that was a nice easy selection for my other coordinate. Okay, so I substitute my y2, y1 here and my x2, x1 here. I get 45 minus 8 over 23 minus 0. Pull out your calculator, and that gives you a gradient of 1.61. And what that actually means is that as the average temperature goes up by 1 degree, the average height of this particular type of tree goes up by 1.61 meters. Question C. All right, determine the equation of the line of best fit. All right, well, this is easy because we know our general form of a linear equation is y equals a plus bx. So the question is, do we know A, the y-intercept, and do we know B, the gradient? Well, let's take a look. Our y-intercept is 8, approximately, but this is an approximate science, so that's good enough. So that's our A value, and our gradient B is 1.61. So we certainly do have enough information. So y equals a plus bx becomes y equals 8 plus 1.61x. And I've been saying things in terms of x's and y's, but if we look back at the question, we're not dealing with x's and y's, we're dealing with average height and average temperature. So the equation is in fact the average height equals 8 plus 1.6 times whatever the average temperature is. Or if we use the actual variables that are supplied, h for height and t for average temperature, we get h equals 8 plus 1.61 t. And now we have a nice little equation that we can use to make predictions. Question D. Use the equation to determine the expected height of a tree in a location that has an average temperature of 8 degrees Celsius. State whether this is interpolation or extrapolation. So those are the 2 words that I avoided defining at the beginning. So we're going to dive into those in a moment. So firstly, let's do the first part of the question. Determine the expected height of the tree in a location that has an average temperature of 8 degrees Celsius. So in other words, when we substitute t equals 8 into our equation here, what do we get for the corresponding h value? Well, you get 8 plus 1.61 times temperature times 8, which is 20.88 meters, if you figure that out on your calculator. Now, the second part of the question is that an example of interpolation or extrapolation? So let's turn back to the graph and let me explain. All right, so here we are. Now, when we constructed our linear model, our equation, the data that we used to construct our equation consisted of these points here. All right, now these points along the horizontal axis, the temperature axis, start at a value of about 5 degrees and go up to a value of about 20 degrees, okay? Now, along the vertical axis, these values start at about, I don't know, what's that, 13 or 14 meters and go up to about 41, 42 meters. So the data that we used to construct our linear equation was bounded both in the horizontal and the vertical axes, okay? Now, we were just asked whether predicting the average height that corresponds with an average temperature of 8 degrees Celsius, we were asked whether that is an example of interpolation or extrapolation. Well, it is an example of interpolation, and that is because T, which equals 8 degrees Celsius, somewhere about here, that is a value that is within the range of data that extends from here to here that we use to construct the model to begin with. Now, if they had asked to what average height would a tree grow in a region where the average temperature is 30 degrees Celsius, which would be over here somewhere, then 30, T equals 30 is outside of the range of T values that we use to construct the model. So that would be an example of extrapolation. And interpolation is more reliable than extrapolation because we can't be 100% sure that these dots here, these points, are going to continue increasing in a roughly linear manner. Who knows? Maybe when the average temperature gets to 25 degrees Celsius, something weird about the biology of that particular palm tree kicks in and the graph just starts to go crazy. Who knows? So the moral of the story is when you are using a value to make a prediction that is within the range of data that you use to construct the model to come up with a linear equation, that is interpolation. When you are using a value that is outside the range of data that you use to construct the equation to make a prediction, that is an example of extrapolation. So, to answer the second part of the question, state whether this is interpolation or extrapolation. It is indeed interpolation. Okay, part E. Use the equation to determine the expected height of a tree in a location that has an average temperature of 25 degrees Celsius. And again, state whether this is interpolation or extrapolation. So we substitute T equals 25 into our equation that we came up with, and we get 48.25 meters. Now, turning back to our graph, when the average temperature is 25 degrees, we are being asked to predict what average height of tree that corresponds to, which would be roughly something above 45, okay? But C equals 25 degrees Celsius is outside of this range that goes from about 5 to about 20, this range of C values that we use to construct the linear equation to begin with. So this is a less reliable prediction, so it's extrapolation. All right, and finally, question F. What average temperature will produce an average tree height of 22.5 meters? Okay, so for this particular question, we're being given a height, an average height, which is 22.5 meters, and we're asked to calculate, using the equation, the corresponding average temperature. We're being asked to make that prediction. Given a particular height, what temperature do you predict that that corresponds to? So it's just substitution once again. We have h equals 22.5 meters, and we substitute that into our equation, which is h equals a plus 1.61 t. And I won't go through the process because that's just a linear equation with one variable, and you've known how to solve those for several years now. Okay, you isolate your t, and you end up with 9.01 degrees Celsius. Okay, thanks for tuning in, guys. Hopefully that made sense. There won't be a video, I don't think, corresponding to the revision. So study hard, and I'll talk to you soon.